A binary search tree is a binary tree with an order applied to it. The value of a left child will be less than or equal to the value of the parent, which is less than or equal to the value of the right child. This property will hold true at every level of the tree. In this video, I will discuss inserting, searching for, and deleting items in a binary tree. Let's start with inserting items. When inserting items into a tree, you should start at the root node and work your way down the tree until you reach a spot where you can store it. The first item is put into the root. All following items are then compared to the root. If a key is less than or equal to the root, it should move down the left subtree, otherwise it should move down the right. At each node this process is repeated, comparing the values and moving it to the left when it is less than or equal to the current node, or to the right otherwise. When nodes are added, they should be given children that are null. Only the internal nodes store values. All external nodes should be null. Binary search trees do not work well when the items being inserted are already in order. It becomes a long sequence of items rather than a good tree. The time it takes to search is based on the height of a tree. Usually this will be big O log n. However, in this case, because it is so linear, this increases to big O of n. Searching for an item in the tree is done in a similar fashion to inserting items. At each point in the tree, we compare the node with the value we are looking for, and move to the left or right subtree depending on the result. This continues until we find our value. If we are searching for a value that does not exist in the tree, we will eventually reach a null node, signifying that the item could not be found. When removing an item that is at the bottom of the tree, that is, its children are external null nodes, we just remove the node and its children, and replace it with a new null node. If the node being removed has two internal children, we need to ensure that the node replacing it will not violate the order of the tree. The easiest way to accomplish this is to replace it with the next value in an in-order traversal of the tree. For this tree, that would be the 5 of diamonds. Notice, however, that after the replacement, we are left with a new hole in the tree. We must recursively replace this one as well. If the next item does not exist, it is also valid to make a replacement using the previous item in an in-order traversal. That concludes my video on binary search trees. Here I provided you with a brief summary of the topics I covered.